Hey guys, let's give this one a try. We're going to study I'll just name it now. Kind of came as a surprise. That was the goal in class. But it's called a thermodynamic cycle. And it's when you do a series of processes in order. And so you have a single mechanism that's then doing different processes one after the other, and you end up in the same place you started. And when you end up in the same place you started, you end up converting one form of energy into another. And that's called a machine, or more specifically, an engine. We're also going to learn this is what a refrigerator is. Maybe you had no idea that was coming. Really cool. I hope you guys see the significance of this, but let's do brief. I'm going to keep this video like succinct, so I might skip some steps. But here we are. And I'm going to do it via um, Desmos. I like it. So right now we have this process going from point one over here to point two over here. See if you can make sense of it. As a bonus, you know, you guys could figure out these equations for a project later. That could be an option. But for now, just look at the graph. And what we want to notice is that, okay, that's point one. This is point two. And it's going this way. By the way, always draw the arrows, always draw your isotherms. We can notice that this is an isotherm here, this is an isotherm here. So from process one to two, it's adiabatic compression. We know it's compression because we started off, this is volume in liters. This is pressure in kilopascals. We started off at atmospheric pressure and 1 liter and compressed it to, this is 0.25 liters. So you can think of like a piston, and this is what we're going to want to think about, right? That's sealed a container full of air. We'll do it on air, right? And it's pushed down, thus doing positive work, thus increasing the temperature, right? Because the kinetic energy went up due to the collisions with the walls, right? The walls were moving. Therefore, the pressure went up, but also the volume went down, and therefore the pressure went up. So the pressure went up, right, like doubly, right, for these two reasons, right? The temperature went up because of this, not because of this, and the volume went down separately, thus both increasing the pressure. So the pressure doesn't increase just as an isotherm. If this was isothermal, it would increase to here. But it's not, it's adiabatic, so we have an extra P increase that ends up bringing it to this number here. Look at that number. How many atmospheres is that? It's about 7 atmospheres, right? Right? 700,000, right? And we can use P1 V1 to the 5 halves. Sorry, not 5 halves. Don't mix that up. I can get it mixed up sometimes too. To the 7/5 equals P2 V2 to the 7/5. And T1, sorry, V1 T1 to the 5 halves equals V2 T2 to the 5 halves. We got it, right? We can get it, right? Just make sure everything's in proper order. Make sure your exponents are in proper order. The exponent is only on the variable that it's next to. It's not on both because there's no parentheses. So you just plug in the numbers, you would get that P2 is this, and T2 is 513.625 Kelvin, which is around, what's that, 240 Celsius? Because you subtract 273. I think it's cool to do that math in your head and get like a Celsius. We could convert to Fahrenheit if we want, but I'm not going to do that. Cool. That's our adiabatic compression. We've compressed it, and the final drawing looks like this, right? We're down to a quarter of a liter, right? And the temperature has gone up, the pressure has gone up. Great. We can also solve. So take those notes, pause it. I'm going to clear everything. That's awesome. And from 1 to 2, right? You can pause that and make sure you can do that. We get that the heat is 0 because it's adiabatic. The work is the delta KE, and they are both equal to 5 halves NR delta T. We can solve for N using that's a P, mhm, using the ideal gas law, and we get 0.04133 moles, right? That number will be constant for this entire time. We will need it for every single step we're going to do. So we plug that in there. Delta T, right, is just 513.625. We want to keep our decimals minus 295. Sorry, the initial temperature was 295. Room temperature. So that means this isotherm is 295, and then this isotherm is 513.625 Kelvin. We get that the work and the delta kinetic energy are, where are we here? 187.718 joules. We'll just round to that. Close enough. We do want to keep all the decimals, and the secret is at the end, right? Very good. So these numbers end up being really important. Great. Let's clear it. Now what we do is this, right? What we do is we add a new point, and we add a new process, and a new isotherm. And in doing so, what we get is a 0.3. And we get the arrow right here. And the challenge is, what is this process? What does it look like? But we want to connect it to the end of the first process, which was this. We had a compressed gas that was heated and super pressured. And what we're going to do is isochorically light a fire underneath it and set it to a final temperature, T3, of 2,400 Kelvin. If the temperature in the fire is 2,400 Kelvin and the fire keeps getting fed, so it doesn't cool down, right? Has fuel, then the inside will have a final temperature of 2,400 Kelvin. That's how heat conduction works, right? The fast, really fast, that's really fast now, right? Really fast moving particles in the fire will collide with the already pretty fast particles here, but they're faster than it. So it's going to heat it up. So we have a heat introduction here, positive Q. We had a work input here. We actually say work in. Work in means positive, right? Heat in means positive, right? So that's just two ways of writing the same thing, right? Point is, heat is inputted, work is inputted. Remember, there's two different ways to change the energy of a gas. This is like the core point of all of this. It's actually pretty straightforward. You can either squeeze the walls, or you can have particles collide, like fire, right? Or heat. That's what we call heat. So you could warm something up, bigger isotherm, by squeezing it, or you could warm something up by lighting it on fire or putting a fire next to it, right? Pretty cool. So we're going to do this isochorically. Notice that volume stays constant at 0.25 liters. The pressure then goes all the way up to, what do we have here? I kind of blocked it. 3,297 point something, right? Uh, kilopascals. Remember, this is kPa, right? pressure in kPa. You can confirm that by an isochoric. Volume is constant, 0.25 liters. Therefore, P3 over T3 equals P2 over T2. So the temperature goes up, the pressure goes up, and you get 3,297 kilopascals. And you realize that's a lot of pressure. Now we're going into like really high pressure realms. And you might say, is this physically possible? It is. This is actually the whole point. This is like a mechanism that people have invented that is very prevalent. And if you figure it out before we finish what this is, that's kind of the point. It's like this is an invention. This is an idea that our entire society is kind of based off of the Industrial Revolution, right? So, for what it is, right? Right. So, cool. We have the ratio to get P3. T3 was given because that's the fire. The fire temperature was this. That was given. All right. And so the question is, okay, what is the heat? What is the work? Well, the work is zero because delta V is zero. There is no work done. It's not compressing. The walls are not moving. So there's no energy added, right? So walls not moving. Careful. Saying delta V is zero is mathematical, but that's not like physical. Physical meaning the walls are not moving is what gives the energy, right? So walls are not moving, great. But then the heat becomes the delta KE, and both of those equals 5 halves nr delta T, and we get that those are equal to 1,619.6996 joules. Great. Again, make sure that math makes sense. Make sure the picture makes sense. We're now adding heat. So what did we do? We have the pressure being increased by work and temperature, and then we have the temperature and pressure increased by heat. Two completely separate mechanisms, but one and then the other. So we're superheating, super pressurizing this thing. Now we have all this pressure. What can we do with it? So we can just keep doing different processes. Like I could have an isobaric go this way, or I could have another adiabatic go this way and like just keep doing it for whatever reason. But one, you do hit limits of whatever mechanism you're actually building. Two, it's not really useful. Like, what are you really doing with it? So, although we could play in this playground, what we're going to do is show what we could do with this like really high pressure. Maybe we could have it push the piston back up. Maybe the piston then now high pressure gets launched back up and we have negative work done on the gas, but negative work means work output on the environment. And the environment in this case is the piston or on the walls, right? So this piston gets thrown up at this like 3.297 megapascals. I gotta write that down too, because that just sounds cool. MPa, megapascals, M for million, right? So if this is kilo, three more decimals would be mega. It just sounds cooler. Anyway, so we're at 32 atmospheres. 33, we'll round. We're actually at 33 atmospheres, 33 ATM approximately, being shot up. That's a lot of force, right? That's a lot of force, right? So if we do that really quickly, that will happen quickly. What type of process is that? Well, if it's quick, there's no time for heat to exchange, right? And it just expands rapidly. Well, we know that that's adiabatic, right? And therefore, we're going to then have a fourth point down here, adiabatic expansion, right? Back to, oh, and we need our last isotherm, back to 1 liter, right? So that's our drawing, right? All that pressure, right? And maybe I can draw what that pressure would look like. Super fast moving particles that are super pressurized because, why were they super pressurized? Super pressurized because P is huge because the temperature is large and the volume was small, right? The temperature was large because we had a heat input. Also, we had work input. The volume was small just because the volume went to 0.25 liters. But really, I would say that temperature increase dominated. I would say, which do you think here dominates? Well, clearly here we had a huge temperature increase, right? T just went crazy high to 2400 Kelvin, just increasing the temperature on its own, where you don't let the volume stay. The volume goes like stays small. It's a pressure cooker. And then you have all this pressure cooking inside and you let it explode, ba-doom, right? And then you get all this work output, negative work, but really it's work output on the piston. We call this the power stroke in engineering, right? This is the power output. You built up this pressure, work input, right? Heat input, right? Positive Q, right? That's work, W in, right? Work input, now heat input, and then power output. So what you can do is figure out that here, the final temperature and the final pressure, again, adiabatic, expansion. You know the formulas. You should get that the final temperature is 1,407, sorry, no, 1,378, excuse me, 378.438 Kelvin is what this isotherm is. So we have the 2,400 Kelvin here, 1,378.438 Kelvin here, 513.625 Kelvin here, and 295 Kelvin here. So we have our isotherms getting warmer, of course, as we go farther up, and we're going just in between them. We're kind of dancing. Hotter, hotter, now colder because we expanded. So it lost some pressure, lost some heat. The pressure dropped from the isotherm because it's getting colder, because the walls are expanding, right? Negative work means temperature drops, which means pressure drops. The volume is larger, which means also pressure drops. Keep it simple. So the pressure drops, but not back to the original because we had added all that heat, right? There's still, 4.7 ATMs, right? 473 kilopascals, about 4.7 ATMs, right? So we can figure out that the work done, right? Heat is 0 for this process. This is now process 3 to process 4, or sorry, point 0.3 to point 0.4. I say like process 3 to 4. That's how we're going to write it. We should get that this, again, 5 halves, same N, right? Because we have the same number of moles, 0.04133, right? Uh, if we calculate that, you should get that equals 877.1445462 joules. Right? There we go. We want that number. So the last process is this. What we're going to do is bring it to its original state like this. Boom. 0.4 to 0.1. And the reason we do that is because then we can do it all over again. And that's what the next video is going to be about. And that's what our class on Thursday is going to be about. Maybe Wednesday we're going to get there. Is that we have 4 and 1. Or if you see this video in future years, it might be completely different days. Who knows? But the point is there'll be another video on that. 4 to 1, we're just going to do pop quiz. What type of process is this? Isochoric cooling. How do we cool it? Well, we had temperature 4 at 1,378.438. And we just connect it to the external room, right? We let the room cool it down and it cools isochorically to back to T1 at room temperature. So this is like the ice, right? This is we call the heat sink, right? Or the heat dump, right? We have a heat output We have a negative Q, right? Dumping this heat, this excess heat we had that we used as a pressure power output, right? Power output going this way. It's the arrow going this way. Okay, we have this power output, right? And now we have this excess heat that we need to dump so that we can start it all over again. Because if we put work in at too high a pressure, then it won't produce the same work out as an efficient mechanism. Ooh, that's the hint, right? So we can solve for this one. What we end up getting, sorry, I need to recalculate real quick. We get 5 halves nr delta t. So I do 5 halves times 0.04133, right? Yep. Times 8.31 times delta t, 1430, sorry, 1730, sorry, 1378.438 minus 295. And we get 900 Q equals delta KE for this process 4 to 1 equals, and work is 0 because it's isochoric, equals 930, that's a 930.27318 joules. And that's negative. And I forgot to say that the other one, this work output was negative 877.1445, something, something, something. All right. That's negative, that's negative. So we put work in, we put heat in, we get work out, we have heat out. That's a cycle. And this piston can then just go back up and down, up and down, up and down. And we can keep doing this. And we are turning heat input into work output. That's the math. I hope that made sense. Hope it did. Maybe you can review what did, what didn't. That was just the math of it. I hope each process individually made sense and like what it looks like what's happening to pressure, temperature, heat, work, and all that good stuff. And yeah, next video will be on how it all looks as like a single like mechanism that just goes over and over again. Have you figured out what it is yet? Piston going up and down, pauses at the top and bottom. It's attached to a crankshaft, pausing at the top and bottom like a simple harmonic oscillator. That crankshaft turns, and you can do anything. There's your gas generator. There's your internal combustion engine automobile. This is called the Otto cycle, not Auto, A-U-T-O. It's O-T-T-O, Otto cycle, and was the inventor of the automobile. Pretty cool. See you guys later.